Good morning, students. We are going to discuss the new topic, that is chemical kinetics. You see, chemical kinetics in this chapter, total in PU, it's having the 8 marks. 8 marks are divided in 1 mark question and 2 mark question and 5 mark. Its marks is divided into 1, 2, 5 marks. The 1 mark, the fourth question, question number 4. The 2 mark, that is 13th question. The 5 mark is 30th. It may be A and B. In this type, the questions will be asked in chemical kinetics. Okay. If you go to the chapter, chemical kinetics. Kinetics, chemical kinetics means chemical. Kinetics means it is a Greek word. It's a Greek word. Kinesis. Kinesis is nothing but movement. Movement means the chemical kinetics is nothing but movement of the chemical reaction or rate of the chemical reaction or velocity of a chemical reaction. You can write anything like movement of chemical reaction or rate of a chemical reaction, or we can write velocity of a chemical reaction. Okay, we will write the definition for the chemical kinetics. Definition. Chemical kinetics is a branch of chemistry. Chemical kinetics is a branch of chemistry which deals with the study of reaction rates, the conditions. Chemical kinetics is a branch of chemistry which deals with the study of reaction rate, the conditions by which the reaction rate can be altered and mechanism of a reaction is called chemical kinetics. You see, the chemical kinetics mainly deals with the rate, or we can write velocity of a reaction, and second, factors affecting rate of a reaction or mechanism of a reaction. Okay, first we are going to talk about this rate of a reaction or velocity of a reaction. You see, first we are going to talk about rate of a reaction. you see, rate of a reaction means it is defined as a change in concentration of any, you see, reactant gives product, you know that. We are taking that there is a change in concentration of a reactant or product in unit time, means a particular time, means already told rate or velocity, okay, means particular time, the unit time, the concentration of a reactant or product changes. Okay, we will define it now. Definition, it is defined as the change in the concentration of any one of the reactant or product. Okay, it changing, okay, product in particular time or unit time. You see, we are taking the reactant and product. If what happens, the reactant, the concentration of reactant decreases, product increases. You are understanding here? The rate of the reaction decreases the concentration of the reactant in unit time. Okay, here rate decreases in the concentration of a reactant in unit time. Rate increases in a concentration of a product in unit time. We will write expression for rate of reaction. You see, rate of reaction expression, we already write that consider reactant gives product. You see, let R1 R2, the reactants, if you take two reactants R1 and R2, means the concentration of reactant in a time t1 and t2 seconds. Similarly, p1 and p2, what will write? The concentration of product in a time t1 and t2 in seconds. You see, the rate is disappears of a R, means reactant fall. If you write for reactant, you see, it will be disappears after the reacting for sometimes. If you take the 10 grams, it gives 5 grams. Okay, if it joins with any another reactants, it gives more, like that. Now we are going to talk the rate of disappearance of a R, means reactant, equals R2 minus R1 divided by T2 minus T1. Correct? No? Reactant, we give written that time. You see, in the disappearance, means disappearance of a reactant, if R2 means reaction of the concentration of the reactant R2 decreases, R1 increases. It is very, very important in a reaction. The rate of the disappearance of a R2 minus R1, we will talk. It is very, very important. I am telling that. You see, this is change, no, we take delta r by delta t. But in rate of disappearance of a reactant you must be write in negative only, negative. The rate can be negative quantity or velocity cannot be negative quantity, so the rate of always multiply by the minus, it becomes positive. When come to, if you write for the rate of dispersions, correct, no, it is negative, means reactant will write that reaction, means in reaction we take the reactant as a dispersants, okay, rate of a disappearance. Reactant, it is a disappearance, it is appearance, okay. Now we are going to write for rate of appearance, rate of appearance of product. Similarly, P2 minus P1 divided by T2 minus T1, we will write delta P by delta T, change, okay. You see the product will be P2 will be increases, P1 will be decreases. The reactant, well, if you take that the reactant, you see in the reactant we taken first reactant will be increases, first reaction, means if you take like sulfuric acid reacts with water molecules, means hydrolysis of acid, you see the first sulfuric acid strongly reacts with the water, correct, no, means water will be decreases when compared to reactant R1. The product 1 will get decreases, product 2 will be more. It is very very important that R2 will be decreases, reactant R1 will be increases, okay. Now we are going to, you see the rate of appearance will be positive, well, rate of disappearance will be negative. It must be very very important. Now we are going to write the graphical representation, graphical representation. It is first we write for means rate of disappearance, means we taking graph x axis, y axis. You see while going to write, first we will write the rate of disappearance of reactant, it is R2 minus R1 by T2 minus T1, shows delta R by delta T, it is negative because it is reactant, okay. See why I am writing for the rate of disappearance. See concentration of a reactant on the y axis, when concentration means time at the x axis. See what happening, we have already I told that in the R1 means initial it is increases, and R2 means concentration of reactant R2 will decreases, correct, no, it will be decreases, goes on decreases. If you write the T and T, we written that R2 R1, correct, no, R2 what I told that it is decreases, it will be increases, correct, no, then R1 it is R1, correct, no, R1 increasing initial, then R2 goes on decreases, okay. Now we will write the plot This is T1, T2. This is R1, R2. Correct? No. This change, dramatical change between T2, T1, it is delta T. What about it goes on decreases? No, this is delta R. It is in negative. Do you understanding here? Negative white, it is decreasing. The slope is goes on decreases. Okay. Well, come to the another graphical representation, that is for rate of appearance. Similarly, I am taking the time on the x-axis, y-axis I am taking the concentration of the product. Concentration of the product. What I told, the product will go first start decreases and again it increases. Correct? No? The graph. This is T1. This is T2. Similarly, P1, P2. This change will tell that it increases. Correct? No, it will be positive. Delta P. Here, delta T. Do you understand the graphical representation? Next, we are going to talk about average rate and instantaneous rate. First we discuss about average rate. You see, we are talking that average rate is nothing but rate of a reaction measured over a long term interval. It shows the long term intervals. Okay, write the definition rate of reaction measured over a long time interval. Means long time interval it is shows. We will write that average rate. This is rate average, small r AV average rate equals, if you write for reactant minus del R by del T. For if you write for product, similarly del P by del T. Do you understand this? The long term, it having a long term. Next, if you talk about instantaneous rate. Instantaneous rate is same, the rate of reaction measured over a short time interval. Short or instant. Okay, we will tell that instant food. Correct? No, like Maggie or something. Did I want to write the definition for instantaneous? Instantaneous, similarly, we'll write the definition here. The rate of reaction measured over a short time interval, or you can tell instantaneous. Okay, similarly we will write RINST, instantaneous rate of reaction gives minus, you see now we are changing del, means del it shows large, del it shows a long, short means we will write small d R by dt. Similarly for product dP by dt. You see del shows larger or long, larger, d shows smaller, larger time interval, shorter or smaller time interval. Did you understanding that average and instantaneous rates? Next we are going to talk about unit of a rate of reaction. What is the unit? You see, if we talk about unit, unit of a rate of reaction or unit of reaction rate. Okay, rate, you see, rate equals change in the concentration of any reactant or product by time taken. Correct? No, change in the concentration of any reactant or product divided by time taken. You see, change in the concentration of any reactant and product means mole per liter. Mole per liter. Time is in the seconds. Time in the seconds. We can write in this expression mole per liter per second. Correct? No? Or we can write mole liter minus 1 second minus 1. For this expression, it is for solutions. Solutions means any solute soluble in a solvent called as solutions. Okay. For gaseous state, for example, for gaseous reactions, the concentration is taken in the terms of partial pressures. Pressures means what happens? Similarly, the rate become partial pressure, means atmosphere, atm by second. We can write atm, atmosphere pressure per second. It is for gaseous. See, there is 2 units for the rate of reaction. In the solutions you can take that solid or liquid, anything. It gives the unit mole per liter per second. For the gaseous, atmosphere per second. Okay. Next, we are going to explain the expression for the rate of reaction in terms of different reactant and products. You see, in the first case we take example mercury in liquid state, chlorine in the gaseous state. It gives mercury chloride in the solid state. You see, here there is no stoichiometric coefficient. You see, I will show here, not given any value. No, if not given any value means it is 1 only. Then we will tell that stoichiometric coefficient of mercury is nothing is there, means it is 1. Similarly, stoichiometric coefficient of chlorine is nothing, means it is 1. Similarly, for mercury chloride, stoichiometric coefficient of mercury chloride, it will not have, we say having same, it has 1. Means in the case, first case, reactant and product will have same stoichiometric coefficient. You see, reactant and product will be same stoichiometric coefficient, same coefficient. If you write the rate of disappearance of mercury and chloride equals rate of appearance of mercury chloride, you see, I will write rate of disappearance of mercury and chloride equals rate of appearance of mercury chloride. If you write the average rate of reaction for this compound is see, I am writing for this compound for average rate of reaction for mercury is reactant, no, negative del Hg by del T. Similarly, if you write for average rate of reaction for chlorine is also reactant, minus del Cl to del T. If you write for product, del HgCl2 by del T. Okay, this, you understand this? Yeah. Next we are going to talk about case 2. In second case we are taking example, that is hydrogen iodide in the gaseous state gives hydrogen gases plus iodine gases. To balance, we are adding 2. Okay, you see here different stoichiometric coefficient in the reactant and the product. Okay, different. Do you understanding here? Stoichiometric of stoichiometric coefficient of hydrogen iodide is 2. Stoichiometric coefficient of the hydrogen is 1. Stoichiometric coefficient of iodine is 1. Did you understanding here? Stoichiometric coefficient of the reactant and product is different. If you write for average rate of reaction for the reactant, you see it is 2. For that we will write minus it is reactant, no, for that minus 1 by 2 delta H hydrogen iodide by delta T. If you write for the product, delta H by delta T equals delta I2 by delta T. You understand this? I am take any one of the product. Okay, you see what I will write. If I am taking any one of the product, that is minus 1 by 2 del Hi by del T equals del H2 by del T. Correct? No? If cross multiplication, minus del Hi by del T becomes 2 delta H2 by delta T. While seeing this expression, what we can write, the rate of the disappearance of hydrogen iodide is equal to 2 times of the rate of the appearance of the hydrogen. Did you understand this? The rate of disappearance of 2 hydrogen iodide equals 2 times the rate 2 times rate of appearance of hydrogen. Okay, we'll take another one simple example, that is example I'm taking nitrogen in the gaseous state, hydrogen in the gaseous state gives ammonia in the gaseous state. To balance we add, okay, if we write for this average rate of reaction minus del N2 by del T equals minus C is 3Z minus 1 by 3 del H2 by del T. Stoichiometric, it is given the stoichiometric 3. For that I have written minus 1 by 3 equals, I am writing for product 1 by 2 del NH3 by del T. I am taking any one of the reactant and one product, minus del N2 by del T equals 1 by 2 del NH3 by del T. Similarly, cross multiplication, what happens? Minus 2 del N2 by del T equals del NH3 by del T. What we'll write here? Formation, the rate of formation of ammonia is equals to, or you can write 2 types. I will write here, see, I am writing first this product, rate of formation of ammonia NH3 equals 2 times rate of disappearance of N2, or else you can write another way, or rate of appearance of NH3 equals 2 times of rate of disappearance of nitrogen. See, in the cases we studied in expressions of rate of reaction in terms of different reactants and different products, we discuss about the 2 cases. Okay, well, like this we can give the expression of the average rate of reaction. Okay, next class we are going to discuss about some problems based on the average rate of a reaction. Okay.